Hi everyone, myself Sneha Deepika. In this video, we are diving into an exciting topic in computer science, graphs and sparse matrices. These two concepts are powerful tools that help us model and solve complex real world problems efficiently. We may not realize it, but graphs and sparse matrices are all around us, from social media to navigation apps to scientific research. In this video, we are going to discuss introduction to graphs, representation of graphs, operations are performed on graphs, and real-world applications of graphs. And same goes with the sparse matrices too. Let's dive into the video to know more about it. Summary and real-world applications of graphs and sparse matrices. Graphs and sparse matrices are fundamental data structures that enable the efficient representation and processing of complex interconnected data. These versatile tools find applications across a wide range of domains, from social networks to scientific computing. Introduction to graphs. What is a graph? Graph is a nonlinear data structure consisting of edges and vertices. Vertices are also called as nodes. When we hear about graph, we classify it into two types, static graph and dynamic graph. In static graph, the structure of the graph remains unchanged throughout its usage, whereas in dynamic graph, the structure of the graph changes over time. Usually, dynamic graphs are more oftenly used, whether it comes to our day to day life or in real world applications. Dynamic graphs are only more oftenly used. So, there are four main types in graphs: directed graph, undirected graph, weighted graph, unweighted graph. Directed graph, in directed graph, edges are unidirectional, whereas in undirected graph, edges are not directed. In weighted graph, edges have some weight or cost assigned to it, but in unweighted graphs, there is no weight or cost assigned to edges. So now comes the representation of graphs. So we represent graph using two things, two methods, adjacency list and adjacency matrices. An adjacency matrix is a 2D array used to represent a graph. In this matrix, each row and column represents a vertex. If there is an edge between vertex x and vertex y, the cell at position vertex x, the cell at a position x comma y is marked as 1. If there is no edge, the cell is marked as 0 or left empty. An adjacency list is a way to represent a graph using a list of lists. In this representation, each vertex has a list of adjacent vertices. For a directed graph, each list only contains nodes with an outgoing edge from that vertex. But for an undirected graph, each list contains nodes that share an edge with the vertex. Adjacency matrices are mainly used for dense graphs, whereas adjacency lists are used for sparse graphs. Adjacency lists are more preferably used because adjacency matrices have less flexibility when compared to adjacency list. And adding and removing vertices involves resizing the entire matrix. And adjacency matrix, of course, takes more space, and space complexity increases. If space complexity increases, time complexity also increases. That is the reason why we use adjacency list more oftenly. Operations on graphs. So usually we perform many operations on graphs. Mainly, to be precise, we perform operations on dynamic graphs especially. So we add vertices, remove vertices, we add edges, and we remove edges. And traversal is also done in graphs. When it comes to traversals, we have two different types of searches: breadth first search and depth first search. And when we can find shortest paths too. For that, we can use algorithms like a star algorithms and more. Real world applications of graphs. Coming to real world applications of graphs, there are many real world applications such as social networks, transportation networks, recommendation systems, bioinformatics, web page ranking, and many more. So social networks. So example of social networks would be platforms like Facebook, Twitter, LinkedIn, Instagram. In a social network graph, people are assumed as nodes and connections. That mean the friendships, or if we follow someone, those are called as connections. We assume that as edges. Algorithm on this graph help identify communities, recommend friends, and even detect influences by analyzing the most connected nodes. Next comes transportation networks.
So, example of transportation networks would be Google Maps, airline networks, public transportation systems. Cities or towns are modeled as nodes here, and the roads, flight paths, and rail lines are assumed as edges. So, shortest path algorithms like A star algorithm and many more are used to find the shortest path from one node to another node here. Similarly, airline networks use graphs to optimize routing and scheduling flights. Recommendation systems, in recommendation systems, it would be some Amazon and YouTube recommendations. So users and products are represented as nodes here, and an edge exists if a user interacts with or shows interest in a product. Using collaborative filtering, these systems recommend items to users by finding similar users or items in the graph. In bioinformatics, molecules like proteins or like molecules, proteins, nuclear neurons and nucleus are all considered as nodes, and their interactions or synaptic connections are called as edges. So graph theory helps understand how diseases spread in cellular networks, or how neural connections affect brain functions, advancing medical research, and etc. So graphs are used in many real world applications like this. We use graphs in web page ranking too. In web page ranking, like example Google's page rank algorithm, web pages are treated as nodes and hyperlinks between the pages are treated as edges. Google uses graph based algorithms to evaluate the importance of each page and giving higher ranks to the pages that are more connected or linked by other high ranking pages. So, and we use graphs in telecommunication networks, like example, internet structure phone networks. Here, routers, computers, laptops, mobile devices are considered as nodes, and connections between them, like cables or signals, are assumed as edges. In fraud detection, also we'll use graphs. For example, banks and financial institutions detecting fraudulent activities here, and in game theory and AI pathfinding, and in many more activities, we use graphs. Here comes sparse matrix. What is a sparse matrix? A matrix with most number of zeros as values is called as a sparse matrix, whereas a matrix with more number of non-zero values are called as a dense matrices. Sparse matrices are generally memory efficient, and we have different specialized operations in sparse matrices. We can perform different types of operations in sparse matrices. They are memory efficient. Storing only the non zero elements reduces memory requirements compared to the dense matrices. Sparse matrix representations. So we can represent our sparse matrix using two different methods: compressed sparse row and three column representation. Compressed sparse row. In compressed sparse row, we represent a sparse matrix using three main arrays: values array, column indices array, and row pointer array. So, compressed sparse row have many benefits. So, three of them are: compressed sparse row format is memory efficient and it ensures faster computation and easy row access is available. Whereas in three column representation, it is also known as the coordinate list format. In a simple way to store sparse matrices by recording only the positions and values of the non-zero elements. It uses three arrays to represent a sparse matrix: values, column indices, and row indices. So advantages of three column representation would be, it has simple structure, it is efficient for building matrices, and it is good for parallel computation. Operations on sparse matrices. So generally, we can perform a lot of operations on sparse matrices, including the operations we perform in matrices generally. So we perform matrix vector multiplications, matrix multiplications. We can transpose a sparse matrix, and we can do many more operations, including all of them. We can also solve a linear system of equations using a sparse matrix. That is why sparse matrix are a bit special. Real world applications of sparse matrices. Generally, sparse matrices are highly efficient for both storage and computation, making them essential across a range of real world applications. So here are some real world applications. We can use them in computational physics, machine learning, image processing, graph theory and network analysis, data science, scientific computing and engineering, and many more. So, in machine learning and data science, sparse matrices are fundamental in handling data sets that have many zero values, especially in high dimensional spaces. That is the reason why we use sparse matrices in machine learning. We can also use sparse matrices in image processing because sparse matrices represent images after transformations like edge detection, where only a few pixels had non zero values. Make it, this sparsity improves storage and computation in image processing tasks. We can use sparse matrices in scientific computing and engineering, where sparse matrices are widely used because of its modeling large scale physical systems and simulations. We can use sparse matrices in search engines and information retrievals, medical imaging and signal processing, robotics and control systems, genomics and bioinformatics too. In academics and finance, we use wide range of sparse matrices just because for portfolio optimization, economic modeling, and many. So sparse matrices are crucial in fields requiring efficient storage and computation for large data sets with limited meaningful data points. They allow for optimized memory usage and faster processing, making them indispensable in applications ranging from social network analysis to medical imaging and machine learning. So, those are the real world applications of sparse matrices. These are the key takeaways we have discussed in our presentation today. Graphs. So, graphs are versatile data structures for modeling relationships and interconnections. And sparse matrices, they are memory efficient representation of matrices with many zero valued elements. That's called a sparse matrix, actually. So applications would be both of them are widely used in social networks, transportations, recommendation systems, scientific computing, and machine learning too. So efficiency, of course, both of them are greatly efficient. We have specialized algorithms and data structures to unlock their performance gains. So yeah, these are the key takeaways we have discussed today. Finally, thank you everyone for listening to my video. Special thanks to my course instructor. I appreciate your time and attention. I hope you found this presentation informative and valuable. Thank you very much.